Good afternoon, everyone. This is Dr. Carlos Morillo from JASCO. Welcome today for this live demo FTIR microscope. Today, I'm going to be using a couple of webcams, so I recommend that you enhance those windows of the webcam so you can have a full view of what I'm doing. Also, I would like to let you know that I'm going to be presenting or demoing two instruments. So there is a moment in the middle of the presentation I'm going to be switching instruments. So I hope that you bear with me. Few seconds, I'm going to be changing instruments. So welcome again for those that keep coming to our live demo today and to our webinars every week. Welcome to those that they are new to our webinars. For those, I would like to make a short presentation and to give you an overview of what I'm going to be doing today. So for those that they don't know JASCO, JASCO is the Japan spectroscopy company known in Japan as a Nihon Bunko. We have our R&D and manufacturing in Hachioji in Tokyo, Japan. Some of our founding members are the famous physicist Yoshio Fujioka and Dr. Shinichiro Tomonaga, who shared the Nobel Prize in Physics in 1975 with Dr. Richard Feynman in quantum electrodynamics. JASCO was established in the US in 1972, and we are currently in Easton, Maryland. This is a line of our products. JASCO covers spectroscopy and chromatography. We have our SPM, FTIR, Raman, BCD, UVVs, near IR, fluorescent, CD, and also HPLC, SFC. For this webinar, for those that didn't attend the past webinars, I recommend to look into the fundamental of FTIR and the fundamentals of FTIR microscopy. So what is this? In this live demonstration, I just want to review some of the features of the two instruments that I'm going to be presenting today. One is the IRT 5200 that have a single detector that is MCT that is cooled using liquid nitrogen and also has a TGS, going to be using mainly the MCT detector. The other instrument is our IRT 7200 that have a 16 element linear array. Those are 16 MCT detectors that they are ordered or organized in a line. I'm going to be measuring some samples today, and the first one is I'm going to be using reflectance mode. This is just ink on a golden mirror. I'm going to be using attenuated total reflectance in the microscope. The sample that I'm going to use is a multi-layer polymer. I'm going to be demonstrating the IQ mapping feature that is especially for static mapping where the stage is not moving, and actually recommended with manual stages. The other feature that I'm going to be showing is the clear view, that this feature allows the user to look through the ATR crystal when the objective is used. And the last measurement is transmittance. I'm going to use also a multi-layer polymer example. So some of the features of the IRT 5200 is that it can be used with our series, the 4000 and the 6000 spectrometer. The 6000 is our high-end research bench. As you can see in the image, in the middle, you can see the microscope. That is that IRT 5000. To the right is the FTIR bench. So we use the light source that comes from the bench. This instrument use a manual stage. Also, it can be upgraded to an auto XYZ stage for high speed measurement. Also, as I mentioned before, has a mid-band MCT detector as a standard. Have different options: TGS, in gas, in B. It can have two detectors. One of the single element detectors can be even exchanged by the user. And this instrument can hold up to 4 different objectives in the automated carousel, and also they are recognized by the software. The IRT 7200 is very similar to the IRT 5200. Is designed for the series 4000, 6000 bench, with the additional feature that can use a rapid scan, use the linear rate as a standard feature, also have the feature that it can exchange one of the single element detector, also have the 4 different objectives that can be exchanged automatically in the software, also in the panel, as I'm going to show in a few minutes, and it can be recognized by the computer. So also with this instrument, since this instrument is designed for imaging, the imaging software is included with this instrument. Of course, we can have also the imaging, IR imaging, ATR imaging, also the function of the IQ mapping. We have the option for dynamic imaging using a step scan, and the multivariate analysis, MCR-PCA, is also included in the analysis of the imaging samples. So the type of objectives that are used in this instrument are Cassegrain. And for my first measurement, that is in reflectance, this is an schematic of the optical path of the IR beam. The IR beam is coming from top. It's going to be reflected in this element that is the primary mirror. Then it's going to be reflected to the secondary mirror, and from there it's going to be reflected to the sample, and the reflection, it goes back by the same optical path. In the sample that I'm going to use for this reflected measurement is an ink dot that you can see here, this black spot there, that is on a golden mirror. And I'm going to use that sample. Is very I'm going to use the golden mirror as a background because it's very reflective substrate. So the next measurement that I'm going to be performing is the Attenuated Total Reflectance, or ATR, but in the microscope. The objective lens is again a Cassegrain, and these Cassegrain have the same primary and secondary mirrors, but the difference is when the light is refracted, or the IR beam is reflected from the secondary mirror and go to the sample, actually it goes to a ATR crystal. For this measurement, the ATR crystal needs to be in contact with the sample. The spatial resolution for this ATR objective is 2.2, and of course is limited by the diffraction limit. We can do the IQ mapping, or the IQ imaging mapping, and it's recommended since the crystal is in contact and we are just going to be moving the optics. There is no reason to raise the crystal and actually place it in another location of the sample. In that way, we avoid the cross-contamination in the sample, and also we avoid the damage of the sample. This is a unique feature for JASCO. And also this since the crystal is in contact with the sample and it can be damaged, we have a pressure control that it doesn't allow to apply more pressure that is needed, avoiding the damage of the crystal and also the damage of the sample. So the other feature related to the ATR microscope ATR is the clear view. In this feature, it's possible to look through the crystal when the measurement is made. So if we combine that capability with the IQ mapping, we can actually have the crystal in contact, move around the optics, and do the measurement without raising the crystal. The traditional way that is done is that the ATR objective is in contact with the sample. If you want to measure another location, it needs to be raised and then change the place and do the measurement. I'm going to show how we can do this measurement without raising the ATR objective. For this measurement, I'm going to use a multi-layer polymer slice. I already sliced it, and we are going to be looking into the cross-section. The last measurement that I'm going to perform is the transmittance. In this measurement, we use two different casa grain. One is in the bottom, that is called the condenser. The optical path is the same. It's going to be reflecting to the primary mirror, then to the secondary, and then this point where we see these two cones in contact, actually that is the focal point where we have the maximum point of focus and actually the maximum point to have a reliable and good IR data. For this measurement of the transmittance, the way to prepare the sample or how we prepare is cutting the slices using the slice master. This is an accessory from JASCO, and we can make very thin slices. And actually, this is our approach or our option for cutting slices. We don't need a microtome. You can easily cut very thin slices with this accessory. When the slice is cut, then it's placed into the two KBR windows, and then they are pressed. And since the potassium bromide, or we usually call it just KBR, is transparent to the IR radiation. When the beam goes through the sample, what we are going to be measuring is only our sample. So the way to prepare is just putting in a mini press plate, and this is the die. We just put the different KBR windows, the sample is in the middle, and then it's just pressed. And this is the very traditional way to prepare KBR pellets for microscope FTIR measurement. So this is what I have for this presentation, and the last slide is just the imaging using the multivariate curve resolution software. And in this software, what the advantage to use this software is only with the collection of the whole image, and also with the collection of the spectra, FTIR spectra, we can automatically extract what are the components of the sample, that especially for complex samples, and we use that information to create FTIR images like you see in this image here. Every color is related to a specific material, like a in this case, principal components. Okay, so now let's change gears. So JASCO we use the Spectrum Manager, and this is the platform for all the instruments for JASCO. And usually you are going to find in the top a tab that say instruments, and here we are going to see all the instruments that they are listed. In this case, we have just an FTIR 4600 bench, and the software that I'm going to be using today is the microscope measurement. In the lower part, we have the analysis software, and this is all the analysis, all the software that we use to analyze the data. Either it's just for the bench of macro measurement or the micro imaging analysis that is for the microscope. So when we open the microscope measurement software, what we see is the first that we see is on top several icons, and today I'm just going to be looking at these 3 here and these 4 icons here. The 3 are multi-point, lattice, and line. Those are the range that we can choose to make the measurements. And the other buttons that I'm going to be talking just today and using is the monitor background, sample, monitor sample, and actually here background measurement and sample measurement. Below that, you can find in the left-hand side the measurement parameters, and these measurements are just for the FTIR instrument. We are going to have like the standard that we can select the number of scan, resolution, the wave range, the wave number range, and the vertical axis that you choose for your sample or background. In the lower part, what we have is the microscope parameters. We have the aperture. This is really important because the aperture is this square that we see here. And what this is going to do is just allow us to make the measurement inside this square, and it's going to exclude all this region. In this moment, the first measurement that I'm going to make is the reflectance, and what I'm looking now is just the golden mirror. This aperture that we see here is 100 by 100 microns, and this aperture can be rotated, or actually we can even change the size. And you can have also favorite size here, and I already have input 100 by 100. I just apply. It's going to move to that. I'm going to be talking about scan mirror when I'm doing the ATR measurement. Objective lens can be changed in the software, illumination, and the reflectance or transmittance mode. On top, we have the spectrum, FTIR spectrum, and in the lower part, the image. Talking a little bit about the instrument, what we have here is the base plate, and actually we can change also the objective in the display that is in front of the instrument. This is a Cassegrain 32X. This is an ATR. We can place up to 4 objectives in this instrument, and this is the 16X Cassegrain. We can control also the light in this panel. Control the pressure in here when the ATR is in use, and we have the joystick that we can move in X and Y, and this wheel, it can be used to control the Z direction. and it can help us for a fine focus of the sample. Okay, in this side is the FTIR bench. The light goes to the FTIR microscope, and we do the measurement. Okay, so this is a automated stage, so we can use the stage to take different pictures. So one of the features that I really like from the software is that, well, starting here, we can take images, and these images can be saved later. One of the features that they are really useful is the multi-image, and we can decide to make, for example, a mosaic. I just decide to make a mosaic of 9x9, 3x3. That is 9 images that have the same field of view of the standard preview that I was looking. So now that we have this mosaic, we can look at here in the multi-image. I can change the size of this image. And what is really useful is that since this is an automated stage, the image is going to record the coordinates. So wherever I double click, the stage is going to move there. So this is the multi-image. So if I double click here, the stage moved there. And when I look into my standard preview, it's going to move to that location of interest. If I double click in this area that is actually out of the field of view, I can go to that area. Of course, we can have a 5x5, 7x7. Even we can specify the area that we want to use, so we can search for different samples. Another feature that I really like is here. It's called the submap, and actually I can click on these in any of these locations, so I can have even a higher or a wider area where I can do the measurement. So since I'm already here, I'm going to do some measurements. I come here and I click in monitor background. So when I monitor the background, I have this spectrum in a single beam, but I have this green bar that it tells me the energy that is going through the detector. That is you can check the health of the instrument or even the detector, and you can have an idea how it's performing during your measurement. Actually, this is a measurement that I do often. Take the measurement on a golden mirror, and with an aperture of 100 by 100, using an MCT, I know that the counting should be something like 30,000. So we take the measurement there. I just set up for 8 scans. It's going to take 3 to 4 seconds to do the measurement. And now I just move to the ink. Also, I can monitor the sample. And that is the FTIR spectrum for my ink. Then I can take the measurement of the sample. Just take a few seconds. And I can send this information or this result to the micro imaging analysis. And usually the results are going to be presented with an FTIR spectrum, the image, and the area where the measurement was taken. Okay. So this is good. Now, this is the measurement for reflectance. Now we are going to go to the measurement using the ATR. For the ATR, we are going to change the lens. Now I'm going to switch to the ATR 5000. The material of this crystal is zinc sulfide. We are going to change the location. I already have the location ready for the multi-layer sample. I have the coordinates. I already know what is the number. I just include it here and just click move. Change the illumination, and we are there in our sample for ATR measurement. We can do a fine tuning there. So the two features that I want to show here is first the clear view and also the IQ mapping. For the clear view, the first thing that I'm going to do is change the aperture. I'm going to change to 25 by 25. I'm going to use the scanning mirror, and with the scanning mirror, what I'm doing is just selecting the area where I'm going to make the measurement. So the measurement, when the crystal is in contact with the sample, all the measurement is going to be performed in this area. So for these also we can take images. So this is the image for my multi-layer sample, and this is a multi-layer polymeric sample. This is the cross section, and actually these two materials that we can see that have different we can say intensity, or one looks in light color and the other is dark. These two are two different polymeric materials. So what we're going to do is just look through the crystal. The stage is going to be lower, just for safety, to don't damage the crystal or the sample. We change the optical path, and what I'm going to do now is just raise the stage. Now the stage is in contact, the crystal is in contact with the sample, and what I did just now is change the optical path for the ATR objective. So this is my aperture, and this area here that is something like 200 by 200 is the area where I can scan. So you can see in this spectrum that we have the signal of one of the polymers. If I move it here, this area looks a little bit dark, and it's dark because it's in contact with the sample. But when I move it to this region, we are going to see that the signature is going to change, and now we see a totally different, or a different spectrum. So I already know what are the areas that I would like to do the measurement, or the location where I want to do the measurement. So I already know that around here there is one polymer, and I'm going to click there. So I'm going to collect the data there. I'm going to collect the data also here. and I want to collect my background here. So now I can also take the image when the crystal is in contact. Now I can add this to this window. I'm going to change the optical path, and then I'm going to do my measurement. So as I said before, as I mentioned before, for every FTIR measurement, you have to have the background. So now the instrument is taking the background, and the background with the ATR is not in contact with the sample. Now the stage is raised again, because now we are going to measure the first sample. So the first sample is in this location, it's a S1, and this is our signature of the FTIR spectrum. This is the second location. Second location was already taken, and we finish our measurement of different locations using ATR crystal. The ATR crystal was all the time in contact with the sample, and we are able to measure different locations looking through the crystal, and even we can move the aperture around and select what is the area that we want to measure. So this was our previous measurement. I already have saved some of the data for you. And this is how the measurements look. We have two different measurements because we have two different polymers. And actually, if I click here, I know that this is the location for the lower part. And we have the other location here where the other polymer is. Okay. If I decide to change this measurement and then make another measurement instead of multi-points, I can also, let me remove these squares here. If I want to make now a lattice, we can now make different a different pattern. Now we have a lattice where we can take this FTIR spectrum of all these regions, and it's going to collect the FTIR spectrum in each square. This is going to take a little bit more time, so I already prepared the measurement, and actually this is a measurement mapping measurement, and this is how it looks. We have the array, and we can click in every array and check which is the spectrum in every square. Since this is an array and we already took the map, I'm going to show you how to create the map. So first, what we do is just send this map here. We are going to create this map based on functional groups. For this polymer, we are going to use this functional group here that is around in the 3200 wave number, and this is related to the OH functional group. For the other polymer, I'm going to use a different functional group, and this functional group is related to the CH bonds or aliphatic functional groups. So we have the two images for the two polymers, and we just overlap them. And now we have an image that we can see a clear difference between the two maps. One looks like green, the other looks like kind of orange or red. And if we want to see how really this image look into our optical image, we have an option that is micro image. And now actually what we do is to overlay the IR image over the optical image. So when I click here, I say okay. And finally, we can fit that image into our micro image. We say okay, and this is how it looks. So we can see here how the polymers and actually this sample is really straightforward because we can see that there is a clear interface between the two polymers, the two layers, but actually we can do the same with more complex samples. But the main takeaway from this image is that we can separate and actually identify different functional groups in a multi-layer polymeric sample. So this is what I was planning to present in the IRT 5200. Now I'm going to move to the IRT 7200. Please bear with me 30 seconds. So now we are in the IRT 7200, and in this instrument, as I mentioned before, is an instrument that is designed for the imaging of fast imaging, and actually it has a 16 linear array 16 linear array MCT detector. So what you see here is the multi-layer sample that it has been sandwiched in between the two KVR windows. And of course, the KVR, the area that we see here is the KVR, and these layers that we can see here are those related to the polymer. I already did some measurements, and I'm going to actually load these. I'm going to load the functional groups that I would like to show today. And the first is the Aliphatic Group. I can open it up, and I'm going to do the same that I showed before. We are going to be doing the mapping using the peak height of the functional group, and actually we can come here and include the name. This is the CH bones or the Aliphatic Group. And we click OK. The second that I want to show is the esta group, and I'm taking these measurements from previous measurement of the same sample. So what I would like to show now is the creation of the maps while I'm doing the measurement. So if I select the specific of the desired functional group, click OK. I can take the background. We can see the background of all the elements that they are doing the measurement. Now I can just change the location, and when I change the location, I'm going to make a mapping using this detector. I'm just going to choose 4 numbers, 4 scans. And also in the webcam, you can see how the stage is going to move, and actually it's a very, very tiny movement. And what you can see in the wave in the webcam is slide that in the middle has the KBR palette. At the same time, while the instrument is doing the scan, you can see how these maps are created. And in this region, we can see that there is, in the Aliphatic Group, this region here that is in blue and lighter blue, and also this region that is here like a little bit red. There is a higher concentration of the Aliphatic Group, and for the ester group that is in the 1735 wave number is this region in the middle. So if we combine these images, this optical image here is what it is, the Aliphatic Group, and actually it's a different polymer. Here we have a different polymer, and in this region we have the same polymer. So if we just want to do a quick check and run only 4 scans, you can decide that, yeah, could be a quick check, but at the same sample I use a higher number of scans. This is 128 scans, and for these scans, when I open them up here, this is how it looks, the spectrum, and very similar to what I showed before. We have an array, and each array we can check what is the let me go a little bit slow. We can check what is in each grid, in each part of this array. We can check what is the FTIR spectrum. So instead of using the peak height, now what I'm going to use is just the part of our software that is called Analysis Wizard, and actually this is very helpful for the novice users. When you click in this menu, the first thing that you are going to find is a window that is going to say water and CO2 reduction. We just click OK because we are going to do the correction of the moisture and CO2 that is present in the environment. Then we are going to do the truncation, and this is just selecting the area where we are going to have the features for the spectrum. Then smooth the data, and actually we are going to do the noise reduction. So the main aim of this software is to optimize the data in order to create a model, and this model is based on the multivariate curve resolution. And when we click in almost the last step in the baseline correction, the data is ready to create this model that is based on chemometrics. And instead of looking into the peak height of a specific functional group, we are looking into the whole data, including not only a specific wave, no, a specific functional group is looking into the whole spectrum wave range, also in the whole image. So with all the information, the model is extracting what are the principal components of these measurement, and is based on that we create the image. So now we have these 2 maps that correspond to each component, and when we overlap them, they look like much more clear and sharp. Of course, if we collect more data, we are going to have a better image. Actually, these algorithm of chemometrics are based on the data that they are fed to create these images. So when we come and see into this on the results of the principal components. These are the two polymers that they are present in this system. So we are going to have in the top right hand the components, below the optical image, and the IR image, that is our map. So with that, this is what I have prepared for today. It was almost 45 minutes. I hope that we have some open now the session for discussion. So I have the first question is if I can make a comment on using low resolution scan and high resolution is like, for example, 16 wave number versus 2 wave number. This is the, of course, if you have 2 wave number, you are going to have a more resolved spectrum. You are going to have more features, but at the same time, you are going to have a lower intensity. So it depends on what is the trade-off. Today I run very high resolution, like 16. I wanted to have all the intensity that I can have, but to have a very nice data. But for example, if you need really to resolve peaks, yeah, you need to use a low wave number. There is a question like, if there is a way to analyze the in situ sample, for example, archaeological samples with tortuous surface. They are very, very challenging, actually. And if I'm honest, and if you can analyze an archaeological sample, maybe I would recommend to use Raman. We have, and actually I hope to demonstrate that in the near future, that for very rough samples we can have very nice mapping and actually very nice measurement of the surface. But for FTIR, due to the resolution and the scattering of the sample is quite challenging. There is a question like, can we see a single crystal and make measurement using this technique? If you want, can you write a little bit more what is a single crystal? It's just pure crystal, or it doesn't have any other phases. Maybe that is what they mean. Yeah, we can overlay optical image with the FTIR image, so that is what we can do. Actually, we have this feature. I'm just showing the answer to this person. We have the what we call the micro image. There is a box to overlay, and now I can overlay the image. Yeah, we can. I can make the library of the compounds that I use today. Is we work with a third party that we use Bio-Rad software and also Bio-Rad database. But if you want, I can contact you and tell you what are the compounds that I measured today. Yeah, you can use library scans for contaminant analysis. We work with, I was saying, we work with Bio-Rad, and in Bio-Rad you can create your own databases if you have a common contaminant, or you can search there what is the contaminant. I haven't worked with very small single crystal, but I guess we can see the reactivity. Maybe if it's in time, you can do maybe a resolve measurement time, resolve time measurement, time resolve measurement. That is a good question. He said, like, would you talk about using low E-glass versus gold slides? I like the gold slides because they can reflect the light, and I use them only for reflectance measurement. low E glass, I use them, but I don't have that much experience doing reflectance. I prefer the gold slide for reflectance measurement. At the end of the story, what the user would like is to have a highly reflectance surface and use it as a background to later try to enhance as much as you can the signal. That's the real reason. Yeah, and that question about reactivity is really good, and actually in the IRT 7200 we can do the step scan there, so we have the dynamic function, so we get in our high-end research instrument like the FTIR 6000, we can have the step scan as an option, and actually we can do a step scan like time resolve measurement in the IRT, actually do the measurement. Wow, this question is really good. Like, you say, what is the sample penetration depth of FTIR microanalysis using ATR compared to Raman microanalysis? Well, the main difference that I have to say is like Raman microscopy is, or the Raman microscopes are confocal microscopes, so you can have you can control the depth of penetration, but also the depth of penetration is going to be based on the type of laser that you use. If you, if I remember well, if you have blue lasers, you are going to have I think it's lower penetration. But in the case of ATR, you are going to have this evidence wave that it will give you a depth of penetration in the measurement, and this is going to be related to the material of the ATR. For example, you have a diamond is a very common material, is very hard, very durable, and the penetration is going to be something like 2 microns. If you are looking to shallow measurements, then you are going to be looking into germanium, and germanium is going to have a penetration depth of something like 650 nanometers. And then you have different materials that they are very common in the market, like zinc selenide. Also, we have zinc sulfide. But the main penetration depth, you are going to have it with the diamond, and that is something like 2 microns. There is a question like, what is the average of the time to carry out an analysis in the 5200? I would say that is, as you see, I just use like 8 scans, and for the reflectance, it was just something like 4 seconds. It's FTIR is a quite fast measurement technique, but if you want to do a mapping, of course, it's going to take more time because you're using just a single detector. If you're talking about like the time that is used to make the analysis, for example, of a mapping, and you are doing it in a 7200, it's going to be much more faster. So it's going to depend on what you want to do. If you want to do single point, of course, it's going to be fast. If you want to do mapping, it's going to take a while. But if you want to have an instrument that it can do a fast mapping, I would recommend the 7200. So we have another question about the incident of light to each objective lens. And I know, for example, the 16 and 32 Cassegrain, they have a different incidence angle, but with this instrument we also have the option of grazing angle that is designed for thin films, and the incidence angle is something like in between 75 and 80 degree, and what you're doing is actually enhancing the light path, and in that way you can measure very thin films. Actually, our standard sample is in the order of angstroms, but if you really want to measure like a thin film, I recommend to put it in a very reflective substrate. Well, okay. Yeah, that is a good question. I think that the PCA showed two. The question is, the PCA indicates two components, yet the image seems to show three. Actually, if I remove the image, you can see that there are only two. I think that the color is just overlapping a little, but actually it's just two. The image is just overlapping a little with the green, but actually there are only two components. And I'm going to point here with my mouse. It's just to say MCR score 1, NCR score 2. There is a question, can you do IQ mapping of a larger area? Can you do IQ mapping of a larger area and piece together a bigger map of surface, like piece together multiple IQ mappings? Yeah, you can add. You can have do the multi-image, and in the multi-image do make different measurements, and of course you can create a mosaic, and actually in that mosaic you can see the different measurement locations. Yeah, I think that at this point I don't see more questions. I target something like 1 hour, so now it's 3 p.m. in the East Coast. I just want to thank you, everybody, for taking your time and listening today this live demo, and I hope that you can join us the next week. Next week, we are going to have Dr. Leah Pandisia coming back with a webinar on the UVV's instrument. And of course, you are going to see these advertised in our LinkedIn, or you are going to have different emails that will get to you. Okay, I think this is all for today. Thank you very much and have a good day.